physics lectures in general physics for medical sciences students by Dr. Hassan Mouridi, Assistant Professor of Theoretical Nuclear Physics at Taiz University, Yemen. Chapter 10, Electricity. Yes. So we are going to hello to everybody and chapter because we have some lack of time. Yes. And we are going to the electricity. Well, talking about the electric charges. What is that? And there are two kinds of electric charges. We are calling them positive and negative. So they have sign, they have sign, yes. And when we're talking about the conductors, something like electrical conductors, that will be that are materials in which some of the electrons are free. So they have some free particles which can be a carriers of the charge. Some of these electrons in the materials are free electrons. That's why we have some free elements to carry this positive or negative electric charge. In the case of electron, it's the negative electric charge, some simple electric negative charge. For example, for the good conductors it could be copper, yes, something like aluminium and silver and gold actually. Yes, but silver is better. Copper, previous time, ancient time, we have some copper wires, yes, silver and copper wires, but they were turned up to aluminium. Insulators, what is that? Like electrical insulator, something special type of in which all of the electrons are burnt atoms, so they're carriers of the you have now these particles, yes, who will bring you a difference of the charge, what carrier of the charge at all. So the electron have the bonds. Every electron in this material, like an electrical insulator, standing still in the atomic grade, and they're bound to their atoms. Yes, so there are no good free carriers of the charge inside the insulator. That's why they are not providing electricity. Examples of good insulator include glass, yes, rubber and wood. So all these electrons inside this material are bound to atoms. They are bound. They are fixed, yes, to atom, if I could say it like that. Semiconductors, the electrical properties of a semiconductors, yes, is something like semi, half conductor, half not conductor, yes. The secret are in the name. So some properties of the semiconductors are somewhere between those of insulators and between the conductors. So in some situations they behave like conductors, in some situation, in some special circumstances, they behave like insulators. Yes, so it depends. Examples of semiconductor materials include silicon, yes, and germanium. Germanium, they have the same, yes, if you think to this type of column inside which is standing silicon, yes, we have also this carbon there, yes. Remember that we have special type of the semiconductor, like special builds of the structure with the carbon, yes, So structured carbon, something like graphene, you know, as a one layer of the net, something like the belts of BGs. Yes, special type of the belts of the carbon. It's also semiconductor. So semiconductors make some from these materials are commonly used in making some electronic chips actually. So silicon, maybe you hear about this name, the Silicon Valley. Yes, it's the special type of the California, the part of the Los Angeles. They are taking up the Massachusetts Technological Institute, where they widely worked inside the electronics chip and nano-electronics, or highly interested in investigation of silicon features, germanium, and so on. So these are very interesting type of materials that are commonly used in making electronic chips. So point charge. We were working inside some physical model which is taking up this term of point charge. Yes, something like point, something like dot, with a special type of the features, with the very special particle of zero size. Yes, and that carries something like etalon of electric charge. Yes, it's the special type of physical model which is we are working inside with this special type of mathematical and physical model, which is refers to a particle, like a little particle, zero size, like dot, that carries an electric charge. So the electrical behavior of electrons, it's well described by modeling them as a point charges, dot, little dot with with a charge, electric charge, and our special charge, it will be unit of it. Electric charge exists like a discrete. Yes, we will say that it's quantized. Yes, so a electric, we will say Q. Yes, there's some special type of Latin letter for this. We'll say that the charge, because we have some all the charges in the sum or number. Yes, the sum number n on E, on some fundamental unit of electron. Yes, so about all this time we will talking about the simple model of electrical behavior of electrons and protons, as well as describe it by modeling them like a point charges, like a little dot particle of the zero sizes with the some etalon charge. And your charge, yes, your charge will be measured like in the size of electron. It's a 1.6 multiplying on 10 in the power of minus 19, yes, coulomb. So coulomb, it's also unit of the charge, it's a coulomb. Yes, but it's huge in comparison with the elemental fundamental charge, fundamental unit of the charge of electron. Electron has the minus sign, and the proton has the same charge, fundamental unit of the charge, but with the opposite sign, because the force is attractive if the charges are opposite sign, and the force is repulsive if the charges are of like sign. Yes, so if they have the same sign, so they will be repulsive. So if you have the united all atom. So we have simplest atom, one electron and one proton. Yes, hydrogen, our H, the first element in this table of periodical table of elements. Yes, so we must have this atom like a simple unite unit of the matter, of something like that. So we need to make this force of attraction together act to make this atom staying still in the long period of time. So we need to have this force so attractive, to being attractive themselves, yes, to attractive to each other, these charges, so they will have the opposite sign. So electron will be with the minus and the proton will be with the plus. Yes, so we will have this type yes together. So I will open. So I will told you about again and again that we have this special feature of electric charge like quantization. So there could be quantized, and it means that the electric charge exists as discrete packets, and all amount of any amount of electric charge you could imagine like the product of the n is the number of your dots, this elementary point charges, yes, and the n multiplying on the elementary fundamental unit of the charge. So this simple expression how to the electric charge exists in the discrete packets, it means that we are multiplying n times the fundamental unit of the charge, the unit of charge of electrons, n times. Yes, it's plus minus, it depends on the sign. Yes, the charge have sign and multiplying on the fundamental unit of the charge of electron E. Yes, it's very important because it's something like fundamental units we are taking everywhere here about the electron. So this special features was invented and talking about first time of it about the electrical forces, how we could measure the magnitude of electric forces between two small charged spheres. Because you know, electron, what is that? It was about like some ancient Greeks even talk about that. Pythagoras, something like some of their of his pupils, they are talking about that. They have noticed that if you if you have friction of the different type of materials, for example, this type of material like electron, yes, they will call special type of the amber, yes, from the big Greek empire of the ancient times, was taking this jewelry from the amber, yes, and they notice that when you're fricted, when you are touch a long time of the wool with the amber, so the amber begins to attract some little parts of the paper, some fur, some smash, yes, so it began to electricize us, yes, and like a hair, clean hair, and you are taking the brush made from the something like rubber or plastic, and the hair began electricizes, yes. So the the first name of the electron of the some particle was arisen in the Greek culture 2000 years ago, when they are talking about amber, because amber from Greek language is the amber actually. Yes, so electron is that name. So the first time when we have some experiments with this special magic, yes, of electrical forces, magnetic forces, how the magnets are influence on some metals, or magnitudes of the electric forces between two small charged spheres, it was known many times ago. But the first man who was trying to make these physical experiments and trying to get some physical and mathematical expression about how to they introduct. There was a Charles Coulomb, yes, and Coulomb, French physicist. There was one of the French Academy of Science for that time. So they are talking about the like electrical force between these two small charged spheres, or we could think about 2-point charges. Yes, about that point charge is a small dot, small spheres. Yes, we are neglected about the dimensions of these spheres. We think that every this dimension could be imagined like a little dot. Yes, so the electrical force between these 2 points with the charge, it's given the introduction about this force, it's given by Coulomb law. So mathematically, we think that electrical force will be equal some coefficient of, yes, electric Coulomb constant. Yes, I given that in presentation. It's 8 multiplying on the 10 in the power of 9 Newton squared divided on the squared. Yes, and to 1 divided on 4p, which is the epsilon 0. It's something like this. Yes, something like special electric constant, something like about this constant more about in the next lectures. But the most interesting what we are thinking about, that this these forces of electrical forces of between 2-point charges, so it depends from the charge of first point charge, yes, first sphere, multiplying on the charge of second sphere, yes, and we are dividing on the distances between them in the squared, yes, in the power of 2. So all these laws about the gravitation force, yes, and this elasticity force, and the mathematically electrical force, they have this special type of dependence. Yes, we have the distance between some points, yes, in the denominator of this ratio all the time. So the distance squared in the denominator. So the force will be depends from the reverse distance squared, or the more distance between the particles, yes, and remember that they are in the denominator, the distance, and it's squared. So they are, when you have changed it twice, yes, the distance is going bigger twice, the force, electrical force between 2 points will be lower in 4 times. Yes, so because 2 in the power of 2 will be 4, and you are dividing or not on about 2 but on 4. Yes, so the force will be lower, yes, decreasing in 4 times. This is a very interesting law about the electrical force, that it radically depends on the distance squared in the denominator. So electric field, what is that? It's a special type of the something like a feature of our universe. We have two type of the matter. Yes, so we have some special type of the value what we built our universe. Our universe built in a two ways, by the matter and by the field. Yes, two type of the something like two type of the material we are talking about. So something like material, yeah, media, all we have in universe, it's media, but we have the something like material, yes, and the field. It's something that we didn't have to get in our feelings. By our feelings we can see something, hear something, touch something, and feel the taste, yes. But field, we have now this possibility to feel the field with some features of feelings of our body, of our organism. But we could set about that we could make some special type of devices which can show us the field exists, because we have something reaction between we have some relations between charges. For example, charges to see at it, yes, and to look at them and how feel the something like special type of experiments, how the some charge could act on the some another charge, yes, or magnet could act on another magnet, or gravitational force of the big object could act on the gravitational force of the smaller object, yes. So we can have making some observations, not really experiments, yes, about our feelings of the possibilities of our body, but some observations how to some special devices could do this. An electric field, it is said to exist in the region of space around the charged object, yes. So we will say that every point with the charge, every little sphere with the charge, or every electron, or in our model every point charge, yes, will be created a region, a sphere, a space around this point charge, yes. It will be electric field, and this charged object will be the source charge, yes, will be the source of this charge, of this electric field. But remember that our distance is standing here in the denominator with the square power, yes. So with the distance, the more the distance, the weaker the electrical force, yes. So the field will be going decreasing tremendously with the distance. So when another charged object, the test charge, enters this electric field, and electric force will be acting on it, the electric force of the source charge will be acting on the test charge, yes. And the electric field vector E, yes, E big with the vector, because it's always have some direction, yes. At the point in space, it is defined as the electric force acting on a positive test charge, Q0, yes. It will be placed at that point divided by the test charge. So the electric field vector, yes, will be the ratio between this electric force, what is acting on a positive charge, yes, F big with the vector Fe, yes, and divided on the amount of this electric in the denominator we will have Q0. Yes, so the positive test charge Q0, which is the place at that point, so we are divided by this test charge every time. Yes, so to make this real, we are just taking this another explanation, the meaning of the electrical force by the Coulomb's law, yes, and we are making equation between our electric field vector E, yes, and our forces, yes, forces of electric field. So we are put inside this equation the electric field, yes, Ki multiplying on G0. G0 in the numerator and denominator are cancelled, so it remains that R squared, yes, R squared in the denominator only, and some multiplying on some R, yes, the R vector here. So in the units of the system, international system of the units, our electric field vector will be dimension in the Newton per Coulomb. Yes, so we need to talk about the electric field more to understand how it works. Yes, so on this picture we could see that this special type of the lines, yes, it's this electric field lines. This is the number of lines per unit area through a surface perpendicular to the lines, yes, and this is amount, this is number of this line per unit proportional to the magnitude of the electric field in that region. Yes, so it's something like the more the field, the more the magnitude of electric field in this region, the greater the amount of the lines here. Yes, the greater will be the number of lines per unit area here through the surface perpendicular A on B surfaces. It will be the magnitude of the field. It will be greater on surface A than on surface B. Yeah. So the greater is the amount of number of lines per unit area through a surface perpendicular to the lines of magnetic field or of electric field here, the magnitude of the field will be greater. The magnitude of the field will be greater on surface A and lower on the surface B here. Yes, what is the cross-sectional area perpendicular to the electric field lines. Yes, so the number of lines of the field lines will show us the this magnitude of electric field of this region. For the positive point charge, the field lines are directed away from the source charge in all the directions. On the first here, on the first picture here, A. Yes, if you have positive proton here, dot point, yes, point charge here with the plus sign, it's your proton, and these field lines are directed away from the source of charge in all directions. And the negative point charge here, it's something like one lonely electron. Yes, very lonely electron. And the field lines are directed toward the source charge in all their directions. So it's not a plate. It's not a plate a figure. Yes, it's just projection of the reality. Imagine that it's a dot in some special kind of the this region, special kind of this space, and it's something like little ball, and the surface of it's spherical. It is sphere. It's little sphere, charged sphere, and these field lines are directed toward into electron, the source change in all directions of the sphere. Yes, and this is on the figure of how projection on the plot on the 2D on the Cartesian coordinates. So the electric field dipole, we will talk in many times about the dipole when we will talk about the electrical cardiogram. Yes, the dipole, we have these 2 points. They are not lonely at all. They have always be in pair, like a woman and a man, like some couple. Yes, and these charges are equal and opposite. Yes, we have plus and minus, yin and yang. Yes, the number of field lines leaving the positive charge equals the number of the lines terminating on the negative charge. Here we have another couple with the 2 pluses. Yes, and this is something like in the right corner. In the right corner we have these 2 pluses here. Yes, something like non-traditional couple. Yes, they have different type, the same charge, but they have different type of the this electrical pole lines. Yes, these charges are equal and positive here. Yes, and the same number of lines leave each charge here, and since they are equal in the magnitude, they have the same something like mirror reflection picture from some axis standing between them. Yes, so they not attract each other, they push each other to the another direction. So absolutely another different picture. And when we have the dipole, yes, it's something like that here. Yes, so the lines are going from the positive charge. It's not a sphere here, it's a more complicated type of the case. Yes, and or the electrical pole line here, electrical lines of the pole going from the positive charge inside to the negative, but they are not equal, and they are not absolutely linear. They began to make this special type of the electrical pole line, electrical field lines of the to build the absolutely different type of the picture. So when we're talking about dipole, the charge will be also point charges, 2 points. They are equal and opposite. The number of field lines leaving the positive charge equals to the number of lines terminating on the negative charge. Yes. when we talking about the electrical, we need to talking about the electrical potential energy. When you are testing the place at your test charge in electric field, it's always experienced a force, and this force will be F electrical will be equal to this amount of the testing charge Q0 multiplying on the this vector of electric field, yes, E. So for a finite displacement of the charge from the A to B, from the point A to point B, we could find the work is done by the field or the charge in potential energy is. So we will talking about the electrical potential. So this difference or change in potential energy will be the delta U will be UB minus UA. Yes, this potential of the point B minus potential energy in the point 8. And we will make the integral from this felt force, yes, experience of force, and it's something like Q0, yes, multiplying on this vector of electric field. When we remember that when we have some finite integral to find the finite displacement, we could make this, we will find the area, the area of curvilinear trapetia under this curvature, yes, of this vector, change of this vector. To find this work is done by to make this finite displacement of the charge from the point A to the point B. The work is done by the field, or the change of potential energy will be the sum of these tiny slices of the this movement, yes, ds, differential s, differential of the your way, yes, of the displacement from the point A, yes, on the bottom of the integral to the point B. Here is your borders of integration. Here is your this bottom and top of curvilinear trapetia, which area you need to find actually. Area under this curvature graph, yes, and we sliced them inside the very little slices inside these layers, yes, and trying to make these layers very tiny, and we are making differential, so we are find the first function, the basement primitive function of the vector of the electric field E, yes, to multiplying to the differential of the displacement, yes. So we need to talk about the electrical potential. The potential energy per unit charge will be, we will find it like the ratio between potential energy divided on unit charge, Q0, test charge, yes. So it will be your electric potential. Electric potential, it will be U divided on Q0. Potential, it's no the scalar quantity, it's no have no direction. The energy, it's also have no direction, it's a scalar, yes. The when you dividing the scalar on the charge, you receive a scalar quantity. Unit of the electric potential will be the volt, yes, and 1 volt, yes, it's another inventor, the great physicist Volta, and Spanish or Italian, I don't remember, excuse me. And we just have this special type of the unit, and we widely use this unit in the normal physical life, because every electrical equipment have this special type of the explanation of his quantities and features on the apparatus labels. We have some volts on the batteries, accumulator, and on every electronical devices on the backstage, on the something like back wall of the device. Yes, so we need to understand how in what conditions the device is working properly. Yes, so we always have this special type, very noticeable electric potential units, volt. It's a joule per coulomb. Yes, so in addition, 1 Newton per coulomb will be 1 volt per meter. It's all taken from some special type of the formulas. But this type of the values, this type of dimensions, 1 volt per meter, it was made historically. It was taking collection in the some dimensions historically, volt per meter. In addition, as a charged particles moving in electrons, we will be talking about the difference of potential energy, difference of potentials. Yes, so we will talking about the electric potential difference between 2 points A and B of the in the electric field. Yes, so we can be simplified the electric field if the electric field is uniform. So the difference potential or electric potential difference will be the potential minus potential of the point A. Yes, at VB minus VA will be delta, another Greek letter. Yes, difference potential, electric potential difference, and we will make this delta U here on the delta V. So our difference, it's our change in potential energy, and it also I'm taking more in the more interesting physics. It's our voltage. Yes, we are also taking we have the same value, volt per meter. Yes, here the units of electrical potential, but the difference of electrical potential could be also measured in volts, and exactly this value you always have on the label of your electrical devices, on your this electrical output devices in your flat, everywhere, on the accumulators, on the batteries, on the every your electrical devices that you collect and into space in your simple life, everyday life. It's exactly this value. Yes, and I just wanted to show you how we managed to take these definitions in the real physics here. So we also summarize these little layers of the electrical vector. Yes, electric field vector here, and this is force of the electric field, as charge. Yes, and we multiplying it on the differential of the displacement, ds. So we need to find this integral. So we need to find, yes, summarization, the function of the electric field through all this displacement, and find the real meaning of the vector of electric field. Yes, electric sorry, inside this electric field, when it's uniform, you will receive the delta V, VB minus VA. It will be minus E multiplying on D. Yes, if your electric field will be the uniform. When then the electric potential due to a point charge at some point R will be V, coefficient of electricity, yes, multiplying on charge divided on some point, the vector point R, yes, distance there, and the electric potential due to several point charge will be equal to Ke to the sum, or from E, yes, it's from 1 to n, the n amount of your electrical point charges, yes, Qi will be divided on the Ri, yes. So do not forget that we are making the sum, so this summarization, or the result of this operation will be Q1 divided on R1 plus Q2 divided on R2 plus till the Qn divided on Rn. This is amount of our simple point charges, yes. The example, how we could think about the electrical potential due to 2-point charges, yes. A charge Q1 equals to 2 micro, the another Greek letter, 10 in the power of minus 6. Minus Q1, it will be 2 microcoulomb, is located at the origin, and the charge Q2, 6 microcoulomb, is located at the another point at distance 0.3.00 meter. Here we have the one charge, it's something like orange or yellow color, and the blue one with another electric charge Q2. And this is always shown on the figure here on the right hand. So we need to find the total electric potential due to these charges at the point P, whose coordinates are 400 meter. Yes, so we built something like Cartesian coordinate here, yes, x and y, with the 90 degrees these grades here, like grades in every 1 meter, yes, x, and every 1 meter y grade. So we need to make something like point P here, yes, point P shown on figure here. When we have coordinates 0, we will receive 0 in y, so the point P is lying on this axis x with the coordinate 4. So we need to find 1, 2, 3, 4, 4 here, and the point P is lying on the axis x. And the when we're talking about the points of the charge 1 and charge 2, they are located in the origin, but the difference between them is a 3 meter, yes, 3 point y axis. If we put inside the 0 point our first body, our first charge Q1, so the second body will be standing on the y 3 point, the y will be at 0, x 0, y 3.00, yes. So it's both of them will be lying on the y axis. Yes, and we just could find the about the total electric potential. So the Vp, your electrical potential due to this charge at point, yes. So we could make it in that point at R1. We need to find the distance R1 and R2, yes. the distance R1 will be 4 meters. Yes, only body align on the axis X, and you just need to find the R2. It's something like diagonal of this rectangle here. Yes, or the from the, you could find it from the distance of the right triangle. Yes, so you have two cathets. You have one cathode 4 meter and another cathode is 3 meters. So one side of this right triangle 4 meter, another side 3 meter. You need to make it, square it and summarize it, and you will receive that the hypotenuse of the another big side of this right triangle will be the sum of the 3 in the power of 2 and 4 in the power of 2. Yes, 3 in the power of 2 9, 4 in the power of 2 16. Sum of them 25. You need to make the square root from it and you will receive the 5 meter. Yes, 5 meter will go in at it will be your R, the distance from the point 2, blue one. Yes, from the point P, you need to find the total in this point. Yes, the coordinates of this point. So the distance between these 2 points will be 5 meters. Yes, very simple. From the mathematical rule of right triangle, you will see them, and you could fill this big formula with the exact total numerical numbers here. Yes, numerical values. So you are oh, I'm sorry, somebody doing some repair maintenance in our flat, so we have different noises here. No, how it going? Okay, so we just need to fill this formula with the numerical values, and you will receive that we will have much bigger value here. So the full total electric potential will be with the sign minus. So it will be minus 6.29 multiplying on 10 in the power of 3 here, volt. Yes, so don't forget that we have the dimension values and we will receive exact result. And when we need to find electric force between the two charges, we just need to make the fill the Coulomb law with the exact numerical values. Yes, here. So we need to, it will be your electric force between two charges. Okay, the capacitors. Capacitors are devices that store electric charge. Where capacitors are used will be include. Yes, the here is that on the picture, not very good photo, but you sometimes haven't seen before this special type of the capacitors, the special that store electric charge. You know, they have some special type of physical and mathematical schools that said that we are some ancient civilization have the primitive capacitors or devices that could store electric charge. Actually, I don't believe in that, but we need to talk about the this special type of the capacitors. It's something like radio receivers, a filter in power supplies, the to eliminate sparkling in automobile here. Yes, something like in our country we call this a candle. Yes, candle inside the automobile ignition. So sometimes we have this special type of energy storing devices in this special type of electronic flashes. Yes, so how make up the capacitor. The capacitor consists of two conductors actually. Yes, so these are called plates. It could be spherical like ancient times ago, and we have even special type of non-conductor between these two conductor layer of dielectric between these two plates, between these two conductors. When the conductor is charged, the plates carry up the charge of equal magnitude and opposite direction. Yes, we have the scheme, the picture of these two type of this special type of conductors with a different sign. Yes, the opposite charges carry out on the plates. Here is it's not a plate, it's some spherical. Yes, it's something like primitive conductor of ancient times. Yes, they put between the plates. It exists between these two plates due to the charge. Yes, so this potential difference exists between the plates due to the charge, and it depends what the media between these two plates. Yes, the most different type of the conductor or capacitor here. And we need to talk about the definition of some special value of gas. So when the capacitor is connected to the terminals of a battery, electrons in the plates and the wires so that plates become charged. And this is on a plate on the right hand of me. I could see that we have two different type of the charges on the two metal plates here with a special area A here. Yes, and this two plate is D, and don't forget that we have special type of device or electric field or something or some accumulator here, some source charge with the plus. Yes, plus sign, plus clemma accumulator are going to one plate with the Q charge. Yes, and another joins going to minus plate with the charge minus Q. Yes, the capacitance C of a capacitor is defined as the ratio of the magnitude of the charge to the potential difference. Yes, between the conductors. So it equals to Q divided on this delta V. Yes, the capacitance of a given capacitor will be a constant, like a feature of this capacitor, like a special type of the value which is define the capacitor. Yes, constant, the same. Yes, this international system of units of capacitance will be farad. Yes, another name of the some great previous time. F, big F, it's your C unit. So the farad is a very large unit actually. So typically in microfarads. Yes, so the microfarads, micro, it's something like 10 in the power of minus 6. Yes, micro. Here is it's a new or mu. Yes, actually we use the mu. It's the in the our European language. Yes, but to put these scratches, to put the labels on every capacitor, it's very difficult to use Greek and Latin letters. So the old Greek alphabet where I didn't use it. So it's this. Here is the m. It's not a milli. Don't forget, nota bene. Yes, remember that. Have this attention that the m. It's not a milli. here is that in the capacitors, when you have capacitance of the capacitor, here is the minus 10 in the power of minus 6, not like milli 10 in the power of minus 3. Yes, exactly in that time, because of label capacitors could be very, very small, but when you have the technicals of the industry, you could not use this special type of Greek of letters or something. It's a little bit another differ this mathematical letter like we have habit. Yes, so it's not only, it's a microfarad EF. It's the 10 in the power of minus 12. Yes, so the parallel capacitor here, it's a C equals to Q divided on this difference of the potential difference, yes, of electric field. So the amount of the charge will be divided on this potential difference, and that before, yes, if you have this electric potential difference between these 2 points, it can be simplified in the electric, and in this case we will think we have used this model, and it will work that we have absolutely equal 2 plates, then we have a very uniform field between these 2 plates of the capacitor. Yes, so we think that field is uniform. Yes, all these electrical field lines are parallel to each other, and they are strictly perpendicular to the surfaces of these 2 plates. So we will think that we have the uniform field, and we could use this formula. Yes, so the capacitance of capacitor for the parallel capacitor, we will have Q divided on ED. Yes, when the D is the distance between these 2 plates. Yes, and the E will be the electric field vector. Yes, between these 2 plates of the capacitor. So you could take it inside the formula and to put inside the definition of the E, the electric field vector. It will be Q D divided on the this epsilon 0 on the area of the capacitor. So it will be the epsilon 0 multiplying on the area of the area of the plate of the capacitor. Yes, these areas of in this case of the each plate will be equal. Yes, the Q will be the charge of the each plate equal with the opposite signs. Yes, signs will be opposite, minus and plus. A dielectric is non-conducting material. Yes, so that when we place it between the plates of the capacitor, the dielectric non-conducting material, that we will between the placet of a capacitor our dielectric, it will be increases the capacitance, and it will increase the magnetic voltage. Yes, so it making much more greater the capacitance and increase the maximum operating voltage when we put inside these 2 plates of the capacitor the dielectric. Yes, dielectric of layer of dielectric inside them. So dielectrics include rubber, glass, waxed paper, and for example air. Yes, and because it's a lack of the carriers of the charge. For the parallel plate capacitor, C here will be K, coefficient of the electricity here, multiplying on the dielectric constant of the material, multiplying on the dielectric another dielectric constant of the material, yes, multiplying on the A of the area and divided on the D, yes, the distance between two plates of the capacitor. Here is the symbol of the capacitor here, yes, two parallel little lines which is intersect this line of circuit of this circuit. An example, parallel dimensions of 2 points, yes, is separated meter thickness of the paper. A special type dielectrical constant of this is a paper K. It's electric constant for the different materials. Capacitance here. So the capacitor will be K multiplied. It's your the vacuum here. Multi of the one plate, yes, you need one dimension of the this rectangle plate, yes, and we are dividing the two plates. So don't forget plates above the dimensions, and yes, we are K3, this epsilon of 885 or minus 12 Coulomb squared multiplying on meter squared multiplying by area 2 multiplying on 3 will be 6. But don't forget that we have centimeter power of minus 2 on 10 in the power of minus 2. It will be 10 in the power of minus 4 meter squared, yes. So we need to divide on the distance thickness of paper, yes. So 1 multiplying on the 10 in the power of minus meters, yes. And then after all transformation of the numbers, we will see that we have result 20 multiplying on 10 in the power of farad. It's the capacitance of your farad, of your capacitor, yes. And we have pico, P, yes, pico, it's 10 in the power of minus 12. Here so will be the 20 on the 10 in the power of minus 12, or the picofarad, yes, picofarad. For lipid bilayer, for some type of lipid membrana of the cell, yes, yes, 2 layers of the lipids is the membrana, biological membrana of the cells of different tissues, yes. We will think that we have some special type of dielectric constant, yes, E pi not 10 in the power of minus 11 farad per meter, and the D distance will be the 50 angstrom. Angstrom it's the something like not even tiny that nanometers. So it's a 10 in the power of minus 10 meter angstrom. It's the ancient German amount to account the distance. It's used in optics, in techniques, in optics. So angstrom we could turn into the 10 in the power of minus 10, and don't forget 15, so another 0, you will receive nanometers, yes, or the 5 on the power of 10 minus 9 millimeter, yes. So thus the capacitance here, yes, per unit area for the unmyelinated axon. Axon is a very long, some very long, big cell of the nervous tissue, yes. With this type of the 5 nanometer thickness, it's something big axon of the maybe some fish or something like that. So it's the capacitance per unit area for the unmyelinated axon at the 5 nanometer thickness will be the capacitance here axon, yes. It will be capacitance of the some axon, yes, of the same area divided on this area, because we have the capacitance per unit area, yes. So we need to divide this epsilon, the electric property, to d, to this distance, yes, nanometer, 5 nanometer thickness, yes. So the first part of the equation, numerator 5 on the 10 in the power of minus 11 farad per meter, and 5 on the 10 in the power of minus 9 meter squared, yes. So you will find that this equation 5 will be cancelled, yes, from the first part on the second part, denominator and numerator, and you will receive that it will be 10 in the power of minus 2 farad per meter squared. This is the capacitance per unit area for an unmyelinated axon, yes, nervous tissue, nervous cells, yes, flated axons. The myelin shells, yes, something like the shell, yes, something like shells and shell, contains a membrane that wraps around the axon and couple 100 times, yes. So could you imagine, it's something like many hundreds of layers, of very thin layers, yes, about around, wraps around the axon. So this special type of the nervous tissue have the special type of shelter, and the membrana that wraps around axon and 100 times, yes, a couple of 100 times. This multi-layer, yes, many times, multi-layer shield, multi-layer arrangement effectively increases the thickness of the lipid bilayer by a factor of 200, yes. So from the thickness of the angstrom is have thickness 1 micrometer here, total thickness, yes, micro, and the 10 in the power of minus 10. So the capacitance per unit area for the myelinated axon will be the capacitance here divided on area. So you divided your dielectric property there to d, the distance, the thickness area, cross-sectional area. It will be 5 on the 10 in power of minus 11 divided to 10 in the power of minus 6, yes. It will be 5 on the 10 power of minus 5 farad per meter squared. Here is that the myelinated axon, yes. The real capacitance per unit area for the myelinated axon, yes. What is the difference between them? In the 3 orders, yes, 1, 2, 3 zeros between them, 1,000 times, yes. Some dielectric constant and dielectric strengths, constant and dielectric strengths of various materials at room. So we have some different type of the different materials, yes, that have different dielectric strengths. all various materials, all this is at room temperature, but we are thinking about air dry. It's very, very noticeable that we have different for the vacuum here. Yes, so the vacuum, it's very, very close. Could you see that it's constant K? Yes, the electric constant and the electric strength. The volt 10 in the power of 6 volt per meter. Yes. So we have this special here with the scratch, so it not have the electric strength at all. Yes. So here the constant K, it's only in the fourth degree here, the fourth order. Yes, 1 2 3 0, only fourth. The order is differ vacuum from a dry air. This is nearly the same, and the different type of tissues, different type of the this various materials, nylon, paper, yes, there's something porcelain, why we have some porcelain isolation, yes, glass isolation, or our special type of devices for electricity, transformators and so on. Strontium titanate, very big, but it's very expensive to make this. It's for the very expensive. Teflon, it's not very bad. Yes, a bakelite or fused quartz. Yes, neoprene rubber, it's also good. That's why it's also some isolation. And water, how big is water? Yes, the electric constant, very big. So the water is a good conductor actually. Water, not clean, not distilled water, because we need to have something. Think of water like the dissolved solution of the salts and some the acids, something like that. It's not only clean water. This we need to talk a little bit more about the electron. Yes, the type of the movement of these charged particles. Yes, here on the picture we have this direct current which we are taking from the works of the Newton and the previous, and for the scientists of the English scientific school. Because we are talking about Faraday works in this special type of the scientific investigation. There was taken historically direction of the current. It's the direction in which positive charges flow when they're free to do so. When they're free to flow, they flow in the direction of the current. It is not true. We always think about the movement of the electron, yes. So, but electron, what the sign of the charge do they have? The sign of the charges of the electron is minus. So we are the direction of the current, of the real current. Yes, a real current of the charged particles, electron, its direction is opposite to in which the positive charges flow when they're free to do so. Yes, but we the real direction of the current is the direction of the minus or negative particles of the electrons. But historically, I will repeat it again and again, we use this type of the formulas and this type of the theory that the direction of the current in the your circuit is the direction in which positive charges or positrons or this special type of the positive elementary charges flow when they are free to flow, they are free to do so. So the most practical application of electricity will deal with the electric currents. Yes. So we will think that we will work in that type of the physical model that describe the reality in that way, that the electric charges move through some region of the space. Then we will have the difference of potential. Then when we have the voltage inside the system, then we have the special type of the forces which is forced to some charged particles or electric charges or electric carriers of the charge, yes, move through some area, from the cross-sectional area, from the some region of the space. So the electric current, like definition of it, is the rate of flow of charge through the some region of the space, yes. And this is like flow of the some special type of liquid of electrons. Could you think about that? Yes, in this model. So assume the charges are moving perpendicularly to surface of area A here. So we have area A, cross-sectional area. Yes, cross-section of the some conductor, for example. Think about like a wire. When you cut it with wire, you will receive that you have some this cross-sectional area of the cylinder, where it's cylinder, and you are cross-sected it and cutted it, and you will receive this round area, yes, perpendicular to this surface. Sorry. If this delta Q, the change of the charge, its amount of charge that passes through this cross-sectional area, surface of the air, yes, in time delta t, in the change of the time from the point 1 t1 to the point 2 t2, yes. So the average current will be the delta Q divided on delta T, yes. The symbol of electric current will be I, big I. So this I average, what the amount of the electric current will be the amount of charge that passes through the area A in time delta T, in the differential of the charge divided on the differential of the time, yes. We have some remains, there remain our something, yes. Return to our explanation of the velocity, of the rate of change of something, yes. The rate of change of the some value. Here is our derivative, yes. So we will have the electric current in this circuit will be the charges are moving perpendicular to a surface area A, will be the velocity of change of the charge, yes, the amount of charge, velocity of change of amount of charge in the period of time, yes. So an ordinary conductor, the direction of the current flow is opposite to the direction of the flow of electron. It's common to refer to any moving charge as the charge carrier. Yes, charge carriers, it could be differ, it could be positive, it could be minus, negative. Yes, electron it's more common, but historically it's that in ordinary there it's common to refer to any moving charge like a charge carrier. And don't forget the direction of the current is the direction in which positive charges are flow when they are moving, when they are free to flow. And the unit of the international system unit of the current is the ampere. Ampere, a big interesting person, another physicist, what is making experiments about the electric field and electric current. 1 ampere. From this definition, we have the electric current is something like rate of flow of charge through some region, or the amount of the charge that delta Q that through the this area A, cross-sectional area of capacitor or cross-sectional area of the conductor in the time delta t. So it's delta Q divided on delta t. And if you have this electric current dimension in the 1 ampere, it's 1 coulomb per 1 second. Yes, 1 ampere it's actually very big, rather big number of the unit of current here. So 1 coulomb per 1 second. Yes, it's a big current actually. Yes, so we need to go to Ohm's law, and maybe that's our time. It's very up. Yes, the Ohm's law, the main law of electricity. Yes, I see the most powerful and more noticeable law of the electricity, our Ohm's law. Mathematically it will call very simple. We are using the simplest equation. Your voltage, it will be equal to the product of the current, yes, multiplying on the resistance. Yes, V is equals to ER. Yes, it's very simple. Or the E will be I. Yes, I. The current will be equal voltage per resistance. Voltage divided on the resistance of this conductor. Yes, so materials that obey Ohm's law are said to be ohmic. Yes, the most metal obey Ohm's law. The materials that do not obey Ohm's law are said to be non-ohmic. Yes, actually. So we have this when we have this graph I and delta V function. Yes, we have the bias here. It's a slope here, 1 divided on R here. Yes, what is how we could imagine the relation between the current and the change of the potential here, our voltage in the system on this circuit. It's a slope of the slope will be 1 divided on R here. Yes, and this R, it's your resistivity. Yes, raw resistivity multiplying on L or divided on A, on the area of the this special type characteristic of the every ohmic material that depends on the properties of the material and of the temperature of the material. This resistance of material depends on its geometry and its resistivity. The C units of resistance are ohms, ohm. The 1 ohm, it's 1 divided on 1 ampere. Yes, it's the definition of the resistance. The resistance in the circuit it's something like how the material resists current, yeah, something like that. You could imagine like you're moving a very crowded place. Yes, it's the and the difference is you're moving inside this something like inside the tube. Yes, inside the tube, wagonette, or inside the some special type of the big crowded place on the some rock concert or something like that. This is the movement of the in the materials with the big resistance. And when you are moving in the late night through the big square, yes, in the center of the city, whereas nobody there, very few people there, it's the material with a low resistivity, because no carriers of the charge and no some artifacts and so on, which is prohibited to you to move. Yes, so to carry out the charge could be freely to move in this some special type of the media. Okay, our time is up. Yes, and we need to finish our lectures. Yes.